Last time, given a function f of x, I defined what I call the derivative f prime of x, which is a limit as h approaches 0 of this difference quotient, f of x plus h minus f of x over h. And, well, more on this is coming, but for example, I mentioned that if you take the derivative, evaluate at x equals a, it gives us the instantaneous rate of change of the function f of x at x equals a. But before we do more with the derivative, we are going to discuss limits, properties of limits, computing limits, things like this. So what's the idea? So suppose you have a function. B and L are numbers. And then as x takes values closer and closer but not equal to b, if the function takes values closer and closer, well, it may be equal to L. L is the limit of f of x as x approaches b. And this is written, the limit as x approaches b of f of x equals L. Now, this is if, so if f takes values closer and closer to this number L, then L is the limit. But we will see limits don't necessarily have to exist. Now, this is really the idea. There is a technical definition of a limit, and it reads like this. For every epsilon greater than 0, there exists delta greater than 0 such that, well, if you have absolute value x minus b strictly between 0 and delta, then absolute value f of x minus L is less than epsilon. But this technical definition is theoretical. It has what's called nested quantifiers. It has an implication, and this is something that is really for more advanced math classes. And so this idea of a limit that x takes values closer and closer to b, f of x takes values closer and closer to L is really what we will use, and not this technical definition. I will leave that to a future class. What I'd like to do is consider this function graphed in red, y equals f of x, and we will find these a through d, these four limits, just using the idea that I have written on the board. And then these four, e through h, are what's called one-sided limits, which I haven't yet written down, but we will discuss when we get to them. So first of all, let us consider this first one. The limit as x approaches 0. So let's look at the graph here. X approaches 0, okay? Then you look up in the function, and what y value are you approaching? Well, as x approaches 0, closer and closer, we are getting closer and closer to this y value, which if you look at tick marks, this is y equals 1. Okay, so this is A. And now we move on to B here. What happens as we approach 2? Well, let me figure out. This is 1, 2, 3, 4, 5. This would be 2. Okay, and now you want x to get closer and closer to 2, and then you look up in the function and see what y value you are approaching. Well, this is problematic, right? Because one could say, well, we're approaching 5. One could say, well, we're approaching 2. But as you move closer and closer to x equals 2, the function value is not approaching only one value. right? That's what we need for the limit, that as we get closer and closer to f of x, must get closer and closer to some number L. And we don't have one number that satisfies this. So this one does not exist, or what you will commonly see written is D and E. Okay, so B, the limit as x approaches 2, does not exist. Let's move on. As we approach 4. Now this is a very interesting one. Maybe I should label 4 here. 4 is not in the domain. You see here this open. This is saying that 4 is not in the domain, or f of 4 is undefined. There is no value for f of 4. However, the limit does exist, because as you approach, as x approaches 4, the function, look, either side, we are getting closer and closer to this y value, which I can label. This y value is clearly y equals 3. So this limit is 3, even though f of 4 undefined. And I could even change my function. Let's suppose I wanted to define f of 4. Well, I could define it here. Now 4 is in my domain, and still the limit as x approaches 4 of f of x is 3, because we take values closer and closer, but not equal to 4. The y value is approaching y equals 3, even though in this example, as I have changed it, f of 4 is 4. Okay, let me erase. Very nice. Now we move on. Next is D. This one, if you see, it's a limit as x approaches -4. So what's happening here? Well, -4 is here. Maybe I'll write that at the bottom. This is -4. Okay. We have a vertical asymptote at -4, but we can still address this question. So here, as x approaches -4, what's happening to the function? Well, look, no matter which way you approach -4, the function is growing without bound, okay? So you could say this, but for a limit to exist, we typically think about a limit being a finite number. Remember, I had B and L are numbers, and infinity is not a number. So you could also say this: to say a limit is infinity is really a fancy way of saying the limit does not exist, because the limit does not exist because it's infinite. Whereas here at 2, this limit does not exist for other reasons, right? That limit is not approaching infinity, but the limit does not exist. So this is 2 different ways you could answer this, but the limit does not exist at x equals -4 as a finite number. Okay, now I would like to move on to E, F, G, and H. Maybe I will erase these and move E, F, G, and H over. So what are these here that we're about to compute? So we have found A through D, and now we move on. Very nice. Well, you notice, before I get into this, this is a limit as you approach -4, okay, and we have discussed. But this, the minus is on the other side, and these are what's called one-sided limits. And, well, as soon as we go back to the whiteboard, I will discuss them more. But what you do is you only look either on the left or the right. And I don't know if you're seeing me or my mirror, so maybe I will just point to the picture. Here, With a minus, this is saying you are approaching 2 from the left, and with a plus, it's saying you're approaching 2 from the right. So in our picture, you only use values here in E, the limit as x approaches 2 on the left, you only use values less than 2 here. So we just track the y value on this side. And you see this limit, the limit from the left, does exist because we are approaching this y value, which I can write it here. This is 5, okay? So the limit from the left is 5. Now, let's look as we go the limit from the right. The limit as x approaches 2 from the right. That's this here. We use values with the plus, use values greater than 2, but approaching. So you're coming down here. And you see the y value, we are approaching y equals 2. Okay, so those are our first two one-sided limits that we have calculated graphically from this picture. And now let's also look at, x equals 4. Here, this is the limit as x approaches 4 from the left. This is the limit as x approaches 4 from the right. Okay, well, here's x equals 4. We come in values less than 4 for the limit from the left. Come up here. Okay, we see it approaches x equals 3, or y equals 3, excuse me. The limit from the left is 3. And similarly, if this is the limit from the right, we come in here from the right and approach 4. We're coming down here on the graph, and you see we are approaching y equals 3. So this limit is also 3. So we saw one-sided limits, and as I mentioned, through calculating one-sided limits at two different x values, we write them like this. We have the limit here. This is the, coming from the left. This is the limit from the left. And you use x less than b to compute this limit. And the way you really want to think about this is if you have a number line and here's b, just as we saw in that example, you come in from the left. You use values less than b. And then you ask, well, what happens to the function value? And then we have the other one-sided limit. This is the limit from the right. And we use x bigger than b. So again, if I draw a number line, here's b, you really come in this direction. And then you ask yourself, what happens to the function value as you approach b from the right? Now, one thing we saw, and this is something that is very useful in calculating the overall limit, which the overall limit, you don't see a plus or a minus. It's just the limit as x approaches b. What we can use here with one-sided limits is if the limit from the left equals the limit from the right, then I'll just say equals some number L. Then the overall limit, or two-sided limit, is this number. So first of all, it exists. The limit as x approaches b of f of x, this exists and equals L. Okay, however, another thing you can use with one-sided limits, maybe I should make this plural. Here's the first one. Here's the second one, is if the limit from the left of f of x is not equal to the limit from the right of f of x, then the overall limit does not exist. Not exist. And you can write D N E. Now, we saw this in our example, right? Let me just remind you what we saw. We just had the following one-sided limits. And if you remember, we also computed the overall limit, but without even having a graph of the function immediately. If you saw this limit from the left and this limit from the right, you would conclude that the overall limit does not exist because the limit from the left is not equal to the limit from the right. And similarly, here, the limit from the left equals the limit from the right. You can conclude, the overall limit exists and equals that number. So you can use this with one-sided limits. And these are very useful, especially when you have piecewise defined functions, which the graph we were looking at in that I created in Desmos was a piecewise defined function. Now here are two really beginning examples, but we will calculate these limits by looking at a graph. And the first one is here k is constant, some number, and perhaps I will draw a picture where k equals 2. And we have some b value. As I've graphed it, b is positive, but it doesn't necessarily need to be. So let's think about what this limit must be. Well, as you come in from the left, y value, clearly we are approaching 2. Similarly, as we come in from the right and approach b, the y value, you see, is 2. This is a constant function, or generally it's k. So what you see here, just by thinking about this graphically, just as we did, this limit is k. Okay? And now let's think about the function f of x is x, and I'm going to do a very similar graph. Here's the graph, y equals x, and I need some value b. Well, we know the point on the graph is b comma b because it's the line y equals x. So now let me get my colors to match here. If we come in from the left, x approaches b, the y value approaches, well, also b, right? And similarly, we approach from the right. X equals b, y value approaches y equals b. And so we see here the limit as x approaches b of just x is b, okay? These are two very beginning ones we can get by looking at the picture. Now, let's list some properties of limits that will help us, just knowing these two, compute many more. My hypothesis here for these properties is that as x approaches b, f of x approaches L1 and g of x approaches L2, and these are both finite numbers, meaning this limit exists as a finite number, this limit exists as a finite number, okay? And then we can say some things. So the first thing I'll say is that the limit as x approaches b of k times f of x, this is k times L1, and here k is some number. It's a constant. Okay? The next property is about if you take f plus g or f minus g and then look at the limit as x approaches b of either the sum or the difference this would be L1 plus L2 if you use the sum, or L1 minus L2 if you use the difference, okay? What else do we have? Well, if you have the limit of a product, this limit would also exist, and it would be the product L1 times L2. And the final property that I will mention for now, we take f of x divided by g of x. Well, this limit, we would just take L1 divided by L2, provided that L2 is not 0, because, well, different things happen. Well, we know we can't divide by 0, but also I will do some examples that address when we have 0 in the denominator. So this was L1 divided by L2, provided L2 is not equal to 0. Now, these properties are a lot more powerful than they may look. All of them, though, you have to start with the limit existing at b for both f and g, and then you get all these other limits, okay? Now, what will follow? What can we use these for? So we found the limit of x. We found the limit of a constant. So here we can get the limit of x squared, right? Because it's a product. Or we could get the limit of x cubed, which is a product. Or we could get the limit if you add powers of x. Things like this. So really we know the limit of polynomial, say, and let's write that now. If we use, as I was just saying, these properties and these two limits, which we calculated just by looking at the graph, we have that for p of x and let's say q of x, polynomials, the limit as x approaches b of p of x equals, well, it's going to be p of b. So you just evaluate the polynomial at b. Well, you see this happening in both of these. And then we had properties about sums, differences, and products. Okay, and so 1, and then 2, if we take the limit as x approaches b of this rational function, where you take p of x divided by q of x, again, we can just evaluate. But this is provided that q of b is not equal to 0. And as I mentioned, we will do many where q of b equals 0. We'll have to figure out how to approach that type. But quickly, before I do any where you get q of b equals 0, let's look at maybe 2 examples here. If you take a limit as x goes to 4 of, say, x squared minus 2x plus 1, this is a polynomial, it's quadratic, okay? So we can just evaluate. This would be 4 squared minus 2 times 4 plus 1. This is 16 minus 8 plus 1. This is 9. And similarly, let's do a rational function. If we take the limit as x approaches negative 1, say, of x cubed over x plus 2. This is a rational function, polynomial divided by polynomial, and if you evaluate the denominator at minus 1, you don't get 0. So this would be minus 1 cubed over minus 1 plus 2, which is minus 1 divided by 1. This is just negative 1. Okay? So these limits immediately, just by using these 2 limits, well, and properties. Here are 2 limits that we cannot directly use what we could in the first 2 examples. because if you just try to evaluate the rational function at this x value, what happens? So we try to evaluate the numerator, we get 16 minus 16. The denominator, we get 4 minus 4, which we get this. Okay? And similarly, if you look here, evaluate the numerator at 1. 1 minus 1 is 0. Evaluate the denominator at 1. You get 1 minus 2 plus 1, 0. Okay, so we get 0 over 0, in this case 2. And I put it in quotes, 0 over 0, because this is indeterminate. This does not exist. Don't just answer that and walk on, because maybe the limit exists, maybe the limit doesn't exist. You don't know. If you try to evaluate and you get 0 over 0, this tells you you need to do something, okay? And we will learn, well, later in the semester, we will learn a beautiful technique called L'Hopital's rule, where we can address limits where we have something indeterminate. But these, you can use algebra. Okay, what are we going to do here? Well, let's factor and then try to reevaluate the limit. So here, we'll do this one first. This would be equal to, let's factor. The numerator is x minus 4, x plus 4 over x minus 4. Now you can cancel here. We get a limit as x approaches 4 of just x plus 4. Now this is polynomial. We have no problem just substituting x equals 4 here. We get 4 plus 4, which is 8. This limit is 8. And if you want to go back to the picture, let's do, okay, because it's an important, we want the limit at 4. Okay. It's an important idea here. This is a line. I need to go up to 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. It's a line with here, intercept, we have a mx plus b, right? The intercept is 4 and the slope is 1. So we go 1, 2, 3, 4. We are at 8. Okay, but open. Okay. So this, with this open, is this function. So my actual function and the line where this would be colored in agree everywhere except x equals 4. And at x equals 4, the function in black, this rational function, is undefined. 4 is not in the domain. That's why I marked it with a open. But this one, 4 is defined. But certainly we see here, here's 4. This is a graph of my rational function in black. And as we approach 4, really from the left or the right, we are approaching, well, it's supposed to be up here. If I graphed it correctly, we'd be approaching y equals 8. Okay. Now, let's think about this one, which is similar in that you try to evaluate and we get 0 over 0, but we will also, as I mentioned, let's factor. So I will continue in blue here. Let's factor. My denominator factors. We have, what is this? X minus 1. And x minus 1. Now we can cancel off one of the x minus 1s and we get this. Well, now what's happening? Try to evaluate. You get 1 over 0, which is not defined, but it's not indeterminate. It's a non-zero number over 0. And this should tell you the limit does not exist. Let's think about what's really happening, and I will graph this function. So it looks like 1 over x, except we have a vertical asymptote at 1. And here. And then here. we see this limit as you approach 1 does not exist. The limit, well, if you come in from the left, goes down to minus infinity. If you come into the right, it goes down up to plus infinity. But even if they were both going to infinity, as we saw in that example, the limit wouldn't exist because we consider limits to be finite numbers. So this limit does not exist. Okay. 1 over 0 is not anything but as you get closer and closer, what's happening is you have a fixed numerator. It's 1. And you have a denominator that's getting very, very, very small. So the fraction will blow up, well, in absolute value. And it depends which side you're on. It'll either blow up to infinity, or if you come from this side, it'll blow down or blow up to minus infinity, like this. Let me repeat, because this is important. 0 over 0, 0 over 0. Both times, one of them, the limit existed. One of them, the limit didn't exist. So don't just stop if you get 0 over 0 and think that you know what's going to happen. You have to do more work to figure out what's going on with the limit. Here's another powerful theorem we can use to calculate limits. So I've always heard of this. It's called the squeeze theorem. Our book calls it the pinching theorem. Let's see. I've also heard it called the sandwich lemma, things like this. But let's state it however you want to call it is perfectly fine. It says the following. If, let's say, f of x, is less than or equal to g of x, is less than or equal to h of x. And the limit as x approaches b of f of x equals the limit as x approaches b of h of x, and this is some number L, then the limit as x approaches b of g of x is L. So you have these two functions, f is down here, and h, okay? F sits underneath, and h sits on the top, and g sits somewhere in between. Ah, very nice. Let's draw a picture. We have b. We have y is h of x. We have y equals the bottom one, f of x. Okay, these both have limit, well, here will be b. And this will be here. Here is y value L. Okay, so you have one on the top, one on the bottom, then you know something about these two limits and these two functions. Then we have g of x, and who knows what it does, but it sits in between these. And then it continues over here, something sits in between. Well, it's forced, and this is the squeeze or the pinched, or I don't know, bread, and then the filling of the sandwich. It's forced that the limit as x approaches b of g of x must also be this same limit L, okay? Because the one that's greater than or equal to this function has that limit, and one that is less than or equal to this function has that limit, and there's no other choice for the limit of g of x. Okay, now let's do an example of this, and then we will discuss limits at infinity. So what's going to be my example? Let's look at the limit as x approaches 0 of x squared sine 1 over x. This is a perfect function for using the squeeze theorem, because what do we know about the sine? Well, the sine always sits between -1 and 1. So we have maybe I will now use blue. We know x squared sine 1 over x is less than or equal to x squared, because the sine is always less than or equal to 1, and it's greater than or equal to minus x squared. Right? Because the sine sits between minus 1 and 1. So if you multiply that by x squared, which is non-negative, you will get greater than or equal to minus x squared, less than or equal to x squared. And the limit as x goes to 0 of minus x squared is, these are polynomial, we can evaluate. Okay, therefore, by the squeeze theorem or the pinching theorem, the limit as x goes to 0 of x squared sine 1 over x is 0. Okay? And we didn't have to really think about this complicated part, since we knew it was sat between 1 and minus 1. It helped us use this squeeze theorem and figure out the limit. Now let's discuss limits at infinity, which is the last main topic I will get to in this video. And we say the limit as x approaches infinity of f of x equals capital L, provided f of x takes values closer and closer and may be equal to capital L as x grows without bound. And just like the case when you take a limit as x goes to b, and b is finite, if you happen to get a function that is going to infinity as x grows without bound, you could say the limit is infinity, but really this is a way of saying the limit does not exist as a finite number. Okay, now let's discuss some important limits at infinity, which will help us work with, generally with functions. First of all, let's take n bigger than 0, and we will look at two limits, this and well, this one, both of these are powers of x. Maybe I should write this before we address what is the limit. But these are both powers of x. And I could rewrite this as a negative exponent, as x to the minus n, but it's fine, I'll leave it like this. Well, here, n is bigger than 0, okay? And then you could look at the graph, for example, but x to the n will grow without bound. So this limit is infinity. This is growing without bound as x grows without bound. Okay, now this one, and this is an important one, if you take 1 over that, so now you have a fraction, and the denominator is growing without bound, right? Fixed numerator. Well, this fraction is going to 0. Okay? Now, one more class of important limits. Let's say a is bigger than 1. And let's look at the limit as x goes to infinity of a to the x. And let's look at a limit as x goes to infinity of 1 over a to the x. These are exponential functions. If you have a base bigger than 1, and I believe we mentioned this a little bit the very first day, if you have a base bigger than 1, the graph basically has this shape. It goes to the point 0, 1, exponential growth. This limit is infinity. And, well, this, more generally, this is This is an exponential with base between 0 and 1. That's what this function is. And the graph of a function like this, I'll do it right here. It goes to the point 0, 1, as all exponentials do, and then it is, like this. Basically, the shape, exponential decay. So this limit, if you have an exponential with base between 0 and 1, or if you write it like this, 1 over a to the x, where a is strictly bigger than 1, this limit is 0 as x goes to infinity. Okay, now let's do some more involved examples of limits at infinity. Here are two rational functions, and we want to know what happens as x grows without bound. Here, now, how are we going to attack this? What's happening? You can think about the numerator is growing without bound, denominator growing without bound. Okay, now what do you do? Well, what we can do here is divide by the highest power of x. Well, I will typically divide by the highest power that I see in the denominator. Divide every single term by x to that power. Okay, so here, the highest power I see in the denominator is x cubed. If I divide everything by x cubed, this is 3. Maybe I'll do this one in 2 steps. And then like this. Right? And then you can simplify this using properties of exponents. I could have written this term as 3x cubed over x cubed, and this term 6x cubed over x cubed, but these two I went ahead and simplified. But this one I can write as 4 over x squared. Okay, now what's happening? This is where we use what I had right here. This power of x, this is x squared, 1 over x squared, or 4 over x squared. The denominator is growing without bound. This is approaching 0. And here, 1 over x cubed, or 5 over x cubed. The denominator is growing without bound. Fixed numerator. This goes to 0. And then, well, what happens? This is fixed, it goes to 3 minus 0 over 0 plus 6. Let's write this. So the limit is 3 minus 0 over 0 plus 6, which is 1/2. Okay, now here, same idea. Numerator and denominator are both growing without bound, but we can divide every term by x to the highest power that we see in the denominator. This is the limit as x goes to infinity. This will be 2x to the 9 over x to the 8 plus 6 over x to the 8. Divided by minus 1, which is minus x to the 8 over x to the 8. Then we have plus x squared over x to the 8 plus x over x to the 8. And now we use our properties of exponents. This is 2x plus 6 over x to the 8 divided by negative 1 plus 1 over, this would be x to the 8 minus 2, and then x to the 8 minus 1 is x to the 7 in the denominator. Now we're in great shape. This term, 1 over x to the 8, goes to 0, and so does 6 over x to the 8. This term and this term similarly approach 0 as x grows without bound. This is just minus 1. Now, so what happens as x grows without bound? This function behaves like 2x over minus 1. But x is growing without bound. This is approaching, well, negative infinity, or you can also say does not exist as a finite number, okay? Our last two limits at infinity for today, here and here, and both of these have exponentials in them. Here you see the numerator and denominator are both growing without bound, but this idea that we just had when we had rational function or polynomial divided by polynomial works here. Well, I could divide everything by 5 to the x, but in this case, I can also just break this into a sum because I have one term in the denominator. So this would be, well, this is 2 over 5 to the x plus 4 over 5 to the x. This part, this is exponential with base less than 1. This part goes to 0. This part is another exponential with base less than 1. This part, maybe I'll write it in red, also goes to 0. So this goes to 0. This goes to 0. And so this limit is 0. Okay, now over here, this one is a little bit different because we have the cosine. And the cosine oscillates. Well, we know the cosine, it just keeps doing this forever, oscillates. But this is a very nice function for the squeeze theorem. So what can we squeeze this between? Well, it's very much like the one when I had sine, what was it, sine 1 over x. Here, I know that cosine is between 1 and minus 1. And so then, like this. Now, as x grows without bound, here to 0, here to 0, because the denominator is growing without bound. Fixed numerator. And so by the squeeze theorem or pinching theorem, we get that the limit, oh, well, I'll write it here. X goes to infinity of cosine x over e to the x is 0. So now we have an answer, okay? Now we will continue discussing limits in the next video, the next lesson. This will be when we introduce the idea of continuity and the intermediate value theorem, and then we will also compute some more limits.